And of course, there are symbols, typically symbols, and we count blank space always as a symbol. There are symbols written on the tape. At the beginning of a computation, typically there'll be a finite number of symbols written on the tape, and you might think of the computation as beginning always with the scanning head scanning the first symbol in the list of symbols that are originally printed on the tape. So you might have something like this on the tape. Think of these as a rather primitive notation for numbers. A single 1 means 1, 3 tallies means 3. So this says 1 plus 3. And the machine has just started by scanning this 1, and then it moved right 1, and it's now scanning this plus and thinking about what to do. So in addition to having, for any given Turing machine, you have a tape, you have a scanning head, you have a symbol from a finite, you have symbols from a finite alphabet, and one of those, including blank space, may be printed, and exactly one may be printed in each square. And apart from the symbols which were typed onto the tape by the operator when he set the problem, when the machine is actually running, further printing can only be done on the square which the scanning head is scanning. So, for example, one way in which this machine might operate, I'll give you a program for doing that in a minute, is if it's scanning this plus and in the appropriate state, it might erase that plus and print a 1 instead. And then when it's done that, it might then go into state which says it go back to the beginning, so it finds a blank, and then move back. So now it's identified the beginning of the string and erase this one, and then go into a rest state, a state in which nothing happens ever. That would be one way of adding. And in fact, here's a program for doing that, exactly that way. The key point is that a Turing machine is completely described by a machine table. Now, there's some confusion, and mathematicians often think of the Turing machine as the table, which makes the machine an abstract object. I prefer to think, and this was Turing's contention, the Turing machine is a concrete realization of the machine table. So, of course, from a mathematical point of view, machines that have the same machine table are identical. So here's a sample machine table. It's a table for doing exactly what I just described, for adding in this rather primitive notation. So you see here, you have 3 symbols, which are called S1, S2, S3. Notice that the machine table has as many rows as there are symbols in the alphabet. That's always finite. One of them is always the blank space. And it has many columns as there are states, as the machine is supposed to have computationally relevant states. So this machine, the machine with this table, is supposed to have 4 computationally relevant states, of which the 4th one, D, is a rest state. You can tell it's a rest state because you notice C here means continue scanning the same square. The fact that you have a C in every instruction in this column means that if the machine is ever in state D, if the machine is in state D, it stays in state D, no matter what it's scanning. If it's scanning symbol S1, which is the first symbol to 1, it prints an S1, which has the effect of not changing what was on the tape. It continues scanning the same square, and it stays in state D. If it's scanning S2, it prints S2, which is to say it doesn't change anything. It doesn't move left or right. It centers, C for center, and it stays in state D. If it's scanning S3, again, it prints S3, which doesn't change anything. It centers, which doesn't change anything, and stays in the same state. So D is a dead state. If you ever get into state D, you never get out of it, and you never do anything. It's the rest state, as the name implies. Now, the other states are the active states. If the machine is started scanning a 1, and in state A, which is the state we imagine the state being in whenever it starts the computation, it goes right 1 square and stays in state A. So if it hits another 1, it'll it'll print that 1 back and go right again. So if you have a row of 1s, the machines will go tick, 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 leaving those 1s, staying in state A, but hunting. It keeps moving to the right until, if it's a properly formed problem, it hits a plus. When it hits a plus in state A, it says, aha, that's not indicated. It replaces the plus with a 1, goes into a new state B, and it goes left. And if the machine, the machine, let's say, will now hit a 1, because it just moved right onto the plus row, at least 1, 1. So when it's in state B and it hits a 1, it leaves the 1 and continues going left. So eventually it hits a blank, because there are only a finite number of symbols on the tape to begin with. And when it's in state B and it hits a blank, it leaves that blank and goes back right, but now in a new state, C. So now the machine hits the first 1, the very tally that it began with, but when it hits this 1 the second time, it's not hitting it in state A, it's hitting it in state C. And when it hits this 1 in state C, it replaces it by a blank. It erases it and goes left and goes into the rest state. So this machine will do what I described. If you give it a problem like 1, 1, any number of 1s, plus 1, 1, 1, 1, it'll add correctly. And the way it adds is by moving to the right till it hits that plus, replaces that plus by a 1, moving to the left till it hits a blank, goes into state B, goes back to that first 1, erases it, and goes into the rest state. The amazing thing is that any computer at all, anything that any computer at all can do in principle can be done by some Turing machines. In fact, there's this one single Turing machine called the universal machine with a machine table which is, and at least some universal machines have not very big machine tables, which can, given enough time, do anything any computer at all can do. Now the important thing is, what do you mean by a computational Turing machine state? The answer is, to know what a Turing machine state is, I have to do what I just did. I have to tell you what a Turing machine is. I have to say what the formalism is, what a machine table is. And then I say, anything whose behavior can be, under a reasonable idealization, can be described by this formalism as a Turing machine, and the relevant states are its computational states. So what's the upshot? Okay, well, this just finishes what I just told you. The machine I described, if the tape originally read 1, 1 plus 1, 1, 1, the machine adds in the way I just described. I just explained what a Turing machine is, and ipso facto what a Turing machine state is. But that's quite general. If you had some other formalism, like Church's or Plini's, etc., something analogous would hold. A formalism for computation theory, what used to be called recursion theory, some people still call it recursion theory, defines a kind of device. Device in a very broad sense. A device needn't be a machine, which is the way Alan Turing thought of it. It could be a system of equations. And two, any formalism defines what counts as a relevant state of that device. But what I've been leading up to is the bottom of this transparency, which is that talk of computational states, when no formalism has been specified, is science fiction, not science. We don't know what we mean when we say that psychological states of human beings are functional states in this sense, unless we specify what the formalism is supposed to be. I have a paper that is called Functionalism, Cognitive Science or Science Fiction. I look to see if the book is in your library today, but it isn't. But it's in a new book called The Future of the Cognitive Revolution, edited Oxford University Press, edited by David Johnson and Christina Erneling.